The machine sat in the corner of the Imperial Army Technical Bureau's testing facility in Sagamihara, 40 miles southwest of Tokyo. It was August 1945, and the summer heat made the warehouse unbearable. Lieutenant Colonel Tomio Hara barely noticed. For 3 months, he and his team of Japan's finest mechanical engineers had been dismantling this American M4 Sherman tank, measuring every component, photographing every assembly, documenting every specification. They had done this before with captured enemy equipment, British tanks, French designs, even Soviet machines. Japanese engineers had a distinguished history of examining Western technology and adapting it, sometimes improving upon the original. But this tank was different. Hara stood before the disassembled transmission spread across 3 workbenches, a complex maze of gears, shafts, bearings, and synchronizers. His chief engineer, a man who had dedicated 20 years to industrial machinery design, held a single gear in his weathered hands. The gear measured perhaps 6 inches in diameter, its teeth precisely cut and heat-treated to exacting specifications. It was one of dozens required for the transmission to function properly. "We cannot make this," the engineer said. The words emerged quietly, almost a whisper, but they carried the weight of 3 months of increasingly desperate calculations. It was not that they failed to understand how the gear worked. They had measured it to tolerances of hundredths of a millimeter. They had analyzed the metallurgy, the specific alloys, the heat treatment processes, the surface hardening techniques. They knew exactly what this component was and what function it served in the larger mechanism. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was far simpler and infinitely more devastating. They could not manufacture this gear, not to these specifications, not at any meaningful scale, not with the machinery, raw materials, and industrial processes available to the Empire of Japan in the summer of 1945. This was not a story about one gear failing to meet standards. This was about what that single component represented, a window into an industrial capacity so vast, so sophisticated, so fundamentally different from Japan's own, that it challenged every assumption upon which the nation had built its war strategy. The Sherman tank was not superior because of revolutionary design breakthroughs or engineering genius. It was superior because the nation that manufactured it operated at a scale of industrial capability that Japan could not replicate, could not match, and perhaps had never truly comprehended. What these engineers discovered in that sweltering warehouse would echo far beyond technical specifications. It represented the moment when propaganda met precision measurement, when national confidence collided with metallurgical reality, when highly educated men realized that their war had been lost not on distant battlefields but in the factories, foundries, and machine shops of an adversary they had catastrophically underestimated. To understand what these Japanese engineers confronted during those months in Sagamihara, we must first understand what they believed before they began taking that Sherman apart. Japanese military engineers in 1944 operated within a carefully constructed worldview, shaped by 2 decades of military indoctrination and deliberately curated information. They understood that Japan was resource-poor compared to Western powers. They knew American industrial capacity exceeded their own in raw numbers. These facts were not classified secrets or hidden truths. What they had been taught, what permeated every level of Japanese military planning, was that Japanese engineering excellence, fighting spirit, and tactical superiority would overcome crude American numerical advantages. The narrative framework was consistent and pervasive. Americans built quantity over quality. They mass-produced cheap equipment in vast numbers. Japanese craftsmen, by contrast, created precision weapons with meticulous care. American soldiers were portrayed as soft, materialistic, dependent on comfort and luxury. Japanese soldiers were hardened warriors, capable of achieving far more with far less through superior spirit and discipline. This was not merely civilian propaganda designed to maintain morale. This analytical framework shaped how military planners, intelligence officers, and technical experts understood and interpreted the war they were fighting. Lieutenant Colonel Hara had graduated from Tokyo Imperial University in 1928 with a degree in mechanical engineering. He had spent the 1930s working directly on tank development programs, contributing to Japan's effort to construct a modern armored force capable of competing with Western militaries. He had studied German tank designs extensively. He had personally examined Soviet equipment captured during border clashes in Manchuria. He had reviewed classified intelligence reports on American and British armor developments. This was not an uninformed man operating in ignorance. He was part of Japan's technical elite. Japanese tank development had followed what appeared to be a logical progression based on the nation's strategic requirements and resource constraints. Japanese tanks were consistently lighter than their American, British, or German equivalents because they needed to operate across terrain where bridges could not support heavy vehicles and logistics networks could not sustain massive fuel consumption. Japanese doctrine emphasized mobility and surprise over raw armor protection. Their main guns were deemed adequate for engaging the light Chinese tanks and fortified positions they expected to encounter primarily in mainland Asian campaigns. The Type 97 Chi-Ha medium tank, which served as Japan's primary armored vehicle during the early war years, weighed 15 tons and mounted a 57mm main gun. For campaigns in China and initial Pacific operations, it had proven perfectly adequate. When combat experience demonstrated the need for heavier armament against improved Allied armor, Japanese engineers responded with the Type 3 Chi-Nu, mounting a 75mm gun with enhanced armor protection. Development continued with the Type 4 Chi-Tu and the ambitious Type 5 Chi-Ri. Each successive iteration pushed closer to Western medium tank specifications and capabilities. Japanese engineers understood they were engaged in a technological arms race. What they had not yet fully grasped was that this competition was not primarily about design philosophy or engineering cleverness. It was fundamentally about the industrial infrastructure beneath those designs, the factories, the machine tools, the skilled workforce, the raw material supply chains, and the electrical grid capacity that made mass production possible. Japan's steel production in 1944 stood at approximately 7 million tons annually. The United States produced 89 million tons in the same period. But these raw numbers alone did not tell the complete story, because Japanese military planners had convinced themselves and their engineers that superior application of limited resources could adequately compensate for this numerical disparity. The belief was rooted in Japan's actual historical experience. They had successfully challenged and defeated Western powers before. They had watched Japanese forces seize resource-rich territories across Southeast Asia in 1941 and 42. They had witnessed the destruction of British battleships, the stunning conquest of Singapore, the humiliation of colonial armies that had seemed invincible. The early war years appeared to confirm that Japanese tactical excellence and warrior spirit could indeed overcome material disadvantages. The engineers at the Technical Bureau had successfully reverse-engineered captured equipment on multiple previous occasions. In 1943, they had examined a Soviet 34 tank in meticulous detail, studying its revolutionary sloped armor configuration, its powerful 76mm gun, and its robust Christie suspension system. They had analyzed its diesel engine, its ballistic protection characteristics, and its cross-country mobility. They understood what made the 34 such a formidable fighting vehicle. Some design elements directly influenced subsequent Japanese tank development. The Chi-Ri incorporated lessons learned from examining the Soviet machine. When Sherman tanks began appearing in significant numbers in the Philippines during late 1944, the initial reaction among Japanese technical personnel was professional interest rather than alarm. The M4 Sherman was already known to them through intelligence reports compiled over the preceding years. It was classified as an American medium tank operating in the 30-ton weight class, armed with a 75mm main gun, protected by armor approximately 50mm thick at its thickest points. On paper, comparing raw specifications, it appeared roughly comparable to Japanese designs like the Chi-Nu, perhaps slightly superior in some individual measurements, but not overwhelmingly so. Not enough to inspire particular concern among men who dealt in numbers and specifications. The Sherman's reputation among Japanese combat forces who had encountered it was decidedly mixed. Some after-action reports emphasized its vulnerability to Japanese anti-tank guns when engaged at appropriate ranges. Other reports noted its mechanical reliability and operational mobility. Tank versus tank combat in the Pacific Theater was relatively uncommon. Most Japanese armor encountered American infantry, fought against fortified positions, or was destroyed by overwhelming American air power before ever engaging enemy ground forces directly. The Sherman was respected as a capable fighting vehicle, but not particularly feared as an impossible challenge. When intact or partially damaged Sherman tanks fell into Japanese hands during the fighting in the Philippines, the decision to conduct detailed technical analysis was completely standard intelligence procedure. Understanding enemy equipment in granular detail was routine military practice. The stated objectives were straightforward and practical. Identify exploitable weaknesses, examine design features that might improve Japanese tank development, and assess whether any components or manufacturing techniques could be replicated to enhance Japanese production. The team assembled at the Sagamihara facility represented the peak of Japan's technical expertise. These were graduates of the nation's most prestigious universities, men who had devoted entire careers to heavy industry, automotive design, and military engineering applications. They approached the captured Sherman with the professional confidence of experts who had solved complex technical problems many times before. Their track record justified that confidence. The initial examination phase seemed to confirm their expectations. The Sherman was undeniably well designed, but it contained no revolutionary breakthroughs that defied understanding. Its sloped frontal armor represented smart, efficient engineering. They had observed similar concepts in Soviet designs. The suspension system was robust and remarkably straightforward in its mechanical layout. The engine was a powerful right radial, originally developed for aircraft, adapted for tank use, a thoroughly practical American engineering solution, perhaps somewhat crude compared to purpose-built tank engines, but undeniably effective in actual operation. The main gun was accurate and powerful, though not dramatically superior to weapons Japanese engineers were already developing for next-generation tanks. Everything appeared comprehensible. Every system could be understood, analyzed, and theoretically replicated or improved upon through Japanese engineering skill. They began the project with careful optimism, approaching it as routine technical intelligence work that would yield useful insights for improving Japanese tank designs. Then they reached the transmission. The transmission assembly of an M4 Sherman tank was a sophisticated piece of mechanical engineering, a synchromesh transmission providing 5 forward speeds and 1 reverse, designed to efficiently transfer power from the 470 horsepower radial engine to the tracks that propelled 30 tons of armored steel across diverse battlefield terrain. When Hara's team first extracted the transmission from the captured Sherman, they followed established procedure: photograph it in its installed position, meticulously document the removal process, label every bolt and connection point for later reference. The transmission unit itself weighed approximately 800 pounds. 4 men and a mechanical hoist were required to lift it safely onto the examination bench. The initial disassembly required 6 full days. This extended timeline was not because the engineers were inexperienced or unfamiliar with transmission mechanics. Hara's chief engineer had personally designed gearboxes for major industrial equipment. Several team members had worked in Japan's developing automotive industry before the war. They thoroughly understood transmission fundamentals, gear ratios, synchronizer mechanisms, shifting systems, bearing placement and lubrication. A transmission is, conceptually, not mysterious machinery. It represents a system for converting engine power into useful motion at varying speeds and torque levels. But as they worked progressively deeper into the Sherman's transmission, carefully removing each component and arranging it in proper sequence for documentation, something began to deeply trouble them. It was the precision, it was the consistency, it was the remarkable quality of every single part, from the largest gear to the smallest fastener. Consider the gears themselves. A functional transmission requires gears that mesh smoothly under tremendous mechanical load, often while rotating at high speeds and subjected to shock loading from combat conditions. The teeth must be precisely cut, not approximately correct, not close enough for government work, but precisely manufactured. The spacing between teeth, the angle of each tooth face, the depth of the tooth root, the surface finish quality, all these factors determine whether gears will mesh smoothly and reliably over thousands of hours of operation, or whether they will bind, grind, and eventually catastrophically fail. The gears in the Sherman transmission were cut to tolerances of 3/1000ths of an inch. The tooth surfaces were hardened to specific depths designed to resist wear while maintaining a tough, shock-resistant core. The metallurgy was sophisticated. Each gear's core remained relatively soft and resilient to absorb impact loads, while the surface was hardened through careful heat treatment to resist the constant abrasion of meshing teeth. This required extremely precise heat treatment protocols, carefully controlled heating and cooling cycles, and absolutely consistent alloy composition in the raw steel. Hara held one of the main drive gears, feeling its substantial weight, examining its machined surface under magnification. The machining marks were barely visible even under close inspection. The heat treatment had created uniform case hardness across the entire surface. Testing it with a hardness gauge at multiple points yielded consistent readings. This particular gear could theoretically be removed and installed in any M4 Sherman being manufactured anywhere across the United States, and it would function identically. How many of these do the Americans make? One of the younger engineers asked the question that hung unspoken in everyone's mind. They all knew the approximate answer from intelligence estimates. American factories were producing thousands of Sherman tanks monthly. Each individual tank required dozens of precisely machined gears of various sizes. The numbers multiplied into staggering totals, millions of precision components, each one requiring sophisticated manufacturing processes and quality control. They systematically laid out the complete transmission in proper sequence across the available workbenches, 17 major gears of various sizes, dozens of roller and ball bearings, complex synchronizer assemblies, multiple shafts, heavy cast housings, numerous seals, and hundreds of fasteners. Each individual component represented multiple distinct manufacturing processes: initial casting or forging to create the rough shape, preliminary machining to approximate dimensions, heat treatment to achieve desired material properties, precision machining to final tolerances, surface finishing operations, and rigorous quality inspection before approval. Hara's team began calculating in earnest, not merely measuring the existing parts that was straightforward engineering work, but calculating what manufacturing capability would be required to reproduce them at scale. This is where the true revelation began to crystallize in their minds. Consider the manufacturing requirements for a single gear. To produce it to Sherman specifications demanded raw material consisting of steel alloy with precise chemical composition, nickel, chromium, and molybdenum in exact percentages, carefully controlled during the steelmaking process. This required steelmaking facilities with sophisticated quality, control, and consistent practice. Japan's steel industry in 1944 was stretched desperately thin, forced to produce increasingly inconsistent alloys as critical resource shortages compelled constant substitutions and improvisation. Forging or casting came next. The gear blank had to be formed to approximate shape through either forging or casting processes. This required proper dies, presses, or forges capable of handling the necessary loads, and skilled operators who understood the process. Japanese heavy industry certainly possessed this capability, but the question became one of scale and priority. The Sherman transmission contained 17 major gears. That was one tank. The Americans were manufacturing thousands. Heat treatment followed. The gear blank required heating to approximately 1500 degrees Fahrenheit, holding at that temperature for a precisely controlled duration, then quenching in oil at carefully managed cooling rates. This created the desired metallurgical structure, a tough, resilient core combined with a hardened outer surface. Japanese facilities could certainly heat-treat parts, but maintaining absolutely consistent temperature control across large production runs presented significant challenges, with coal-fired furnaces and limited instrumentation for precise temperature monitoring. Precision machining represented the critical bottleneck. The gear teeth had to be cut to 0.003 of an inch tolerance. This demanded specialized gear-cutting machines, gear hobbers or gear shapers, equipped with precision arbors, cutting tools manufactured from high-speed tool steel, and highly skilled machinists capable of setting up and operating the equipment. The cutting tools themselves wore down progressively during use and had to be regularly replaced or professionally resharpened, requiring additional supporting infrastructure and skilled toolmakers. Japan's machine tool industry in 1944 was already operating at the absolute edge of its capabilities. Machine tools represent the machines that manufacture other machines: lathes, milling machines, grinding machines, gear cutters, and countless specialized devices. They constitute the fundamental foundation of industrial capacity. A nation possessing a sophisticated machine tool industry can manufacture almost anything given sufficient time and resources. A nation lacking that foundation faces fundamental constraints that cannot be overcome through willpower or determination alone. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese machine tool production had grown substantially during the 1930s, but it relied heavily on imported precision machine tools from Germany, Britain, and ironically, from the United States itself, before diplomatic relations collapsed. When war severed these import channels, Japan struggled increasingly to produce the precision machine tools needed to manufacture precision equipment. The existing machine tools were wearing out from heavy use, and domestically produced replacements were notably crude by comparison to the imported equipment they replaced. One of Hara's senior engineers devoted 2 full weeks to calculating how they might cut the required gears using available Japanese industrial capacity. He was not attempting to design new gears with different specifications, simply trying to determine how to reproduce the American gears they had in front of them. His conclusion was sobering. They would require gear hobbing machines of a type that existed in Japan in only limited numbers, perhaps a dozen machines across the entire country capable of achieving the necessary precision. Each machine could theoretically produce perhaps 4 to 6 gears per day, depending on size and complexity. The Sherman transmission required 17 major gears, plus numerous smaller components. The mathematics became brutally clear. Assuming 5 gears per machine per day as a reasonable average, 17 gears per transmission meant approximately 3.5 days of continuous machine time per transmission. Assuming the machines ran without interruption, never experienced breakdowns, and produced 0 defective parts requiring rework. Japan possessed perhaps 12 machines of the required precision capability. Working at absolute theoretical maximum capacity, these machines could produce transmission components for approximately 1 Sherman equivalent tank per day if they did nothing else, if they never broke down, if all raw materials arrived on schedule, if every single part passed quality inspection on the first attempt. The Americans were producing 1,500 Sherman tanks monthly in mid-1944. That equated to 50 tanks daily, 50 complete transmissions, 50 sets of 17 precision gears, plus hundreds of other finder components, every single day. But the challenge extended far beyond gears alone. The bearings presented their own formidable obstacles. The Sherman transmission employed tapered roller bearings and ball bearings in multiple critical locations, each precisely engineered to handle specific loads and rotational speeds. Manufacturing quality bearings demands precision, grinding of bearing races to create perfectly smooth surfaces, production of absolutely spherical balls or precisely tapered rollers, assembly under scrupulously clean conditions to prevent any contamination, and extensive testing to verify performance under load. Japan's bearing industry certainly existed. The Nippon Seiko Company and several other manufacturers produced bearings for various industrial applications. But wartime bearing production was already fully allocated, stretched to absolute limits, supporting aircraft engine production, naval machinery, and existing tank manufacturing programs. Bearings had become a critical bottleneck strangling Japanese industrial output across multiple sectors. The Imperial Navy and Imperial Army competed ferociously for available bearing production, each service insisting their requirements took absolute priority. Adding Sherman-equivalent transmission requirements would demand expanding bearing production capacity substantially, which meant acquiring more precision, grinding machines, securing more high-quality bearing steel, training more skilled workers, and most critically, time that simply did not exist. The synchronizers presented yet another manufacturing challenge. A synchromesh transmission allows smooth gear changes without the grinding and clashing that occurs when gears spinning at different speeds are forced together. The synchronizer assembly matches the rotational speeds of gears before they engage mechanically. The Sherman synchronizers employed brass cones machined to precise angles with carefully controlled surface finishes. Under load, during a gear change, these cones generated controlled friction to match speeds, then allowed smooth engagement. Manufacturing these components required brass of absolutely consistent chemical composition, precision machining of cone angles accurate to minutes of arc, and careful surface finishing to achieve the proper friction characteristics. Each component told exactly the same story. This was not impossible engineering requiring revolutionary scientific breakthroughs. This was sophisticated manufacturing executed at tremendous scale with consistent quality control. The distinction mattered enormously. Hara's team worked methodically through the entire transmission assembly, component by component, documenting not merely physical dimensions, but the complete manufacturing requirements each part demanded. They filled notebook after notebook with calculations, material specifications, and process requirements. They consulted extensively with contacts at Mitsubishi Heavy Industries, Kawasaki, and other major industrial firms that formed the backbone of Japan's military production. The verdict returned consistently. We could manufacture a few of these components, with tremendous effort and extended time. We could not manufacture them at a meaningful scale. We could not produce them reliably with current resources and facilities. But the transmission represented only one system among many. They examined the engine, a Wright R975 Whirlwind radial aircraft engine adapted for armored vehicle use, producing 470 horsepower. It was remarkably sophisticated equipment featuring precision-machined pistons, carefully balanced crankshafts, complex carburation systems, and aircraft-quality magnetos for ignition. Japanese engineers examined it and recognized immediately that replicating this engine would require aircraft engine manufacturing capabilities that were already operating beyond sustainable capacity, supporting Japan's air forces. They analyzed the electrical system in detail: generator, starting motor, battery, complete lighting system, radio power supply with voltage regulation. Each component represented additional manufacturing chains with their own specialized requirements. The wiring harness alone contained dozens of precisely crimped electrical connections, rubber-insulated copper wire in specific gauges, and standardized connectors designed for field maintenance. These might seem like minor details individually, but multiplied across thousands of tanks, they represented entire factories dedicated solely to electrical components. The suspension system employed vertical volute spring suspension, a relatively simple, exceptionally robust design that nonetheless required precisely manufactured springs, carefully machined bogie wheels with proper bearing surfaces, and rubber track blocks. Japan's rubber supply had become critically short by 1944 due to the loss of Southeast Asian sources. American tanks rode on rubber track blocks that gradually wore out and could be readily replaced during field maintenance. Japanese tanks increasingly used steel track blocks as rubber became unavailable, which dramatically accelerated wear on drive sprockets and idler wheels while making the ride punishingly harsh for crews. Even the armor plate itself told a revealing story. American armor was rolled to consistent thickness specifications, with uniform hardness properties throughout each plate. Japanese armor plate by 1944 varied noticeably in quality. Some production batches rolled thinner than specified to conserve increasingly scarce steel, others exhibiting inconsistent hardness due to irregular heat treatment as fuel shortages affected furnace operations. American welding was highly standardized and consistently reliable across production. Japanese welding quality varied significantly, with the skill level of individual welders and the increasingly poor quality of available welding rod as alloying elements became scarce. By the third month of intensive examination, something fundamental had shifted in the consciousness of Hara and his engineering team. They had begun this project as professional engineers analyzing an enemy weapon system. They were concluding it as men who had glimpsed the true nature of the industrial war their nation was fighting. The surviving fragments of their final technical report, portions of which were preserved in post-war archives, reveal this psychological journey clearly. Early entries remain clinical, technical, and professionally confident in tone. Later entries display mounting frustration, then a kind of numbed realization. One engineer wrote in his personal diary, later recovered, "We are not behind in understanding the principles. We are behind in everything that makes understanding matter in practice." Another team member, a specialist in metallurgical engineering, noted in his working papers, "The American tank is not superior because American engineers are more clever than we are. It is superior because they can afford to make everything well. We must constantly choose what to make well and accept that everything else will be inferior by necessity. The Americans do not face this choice. They simply make everything to high standards." The final report submitted to Imperial General Headquarters arrived in late August, 1945. Its conclusion was devastatingly stark. Reverse engineering the Sherman tank transmission was technically possible in theory, but practically impossible given Japan's current industrial capacity and resource situation. Specific recommendations for improving certain aspects of Japanese tank design could be implemented on a limited scale, but creating a Sherman-equivalent vehicle at production scales approaching American output was fundamentally beyond Japan's manufacturing capability. The report reached headquarters at a moment when such technical conclusions had become tragically academic. American B-29 bombers were systematically devastating Japanese cities with incendiary raids. The Soviet Union had entered the Pacific War, crushing Japanese forces in Manchuria. Atomic bombs had incinerated Hiroshima and Nagasaki. Japan was negotiating the terms of surrender. The question of whether Japanese engineers could successfully copy the Sherman tank had been rendered entirely moot by events. But for the men who had spent 3 months intimately examining that machine, the timing did not diminish what they had learned. They had experienced something that transcended military intelligence gathering. They had undergone a profound revelation about the fundamental nature of the war their nation had been fighting. Lieutenant Colonel Hara survived the war, and according to post-war interviews conducted by American technical intelligence teams, he spoke with careful precision about what the Sherman examination had meant to him, professionally and personally. He described it as the moment when he finally understood that Japan had been simultaneously fighting two distinct wars, a military war of battles, campaigns, and tactical engagements, and an industrial war of production capacity, resource mobilization, and manufacturing infrastructure. Japan had desperately hoped that excellence in the first category could somehow overcome massive disadvantages in the second. The Sherman's transmission had demonstrated to him that this hope was fundamentally an illusion. It was not that individual Japanese products were inherently inferior. Some Japanese military equipment was genuinely excellent by any objective measure. The Type 93 long-lance torpedo was arguably the finest torpedo produced by any nation during the war. Japanese optical equipment was superb, rivaling or exceeding German equivalents. Individual Japanese engineers and craftsmen were as talented and skilled as their counterparts anywhere in decunat of the world. The problem was systemic, structural, foundational in nature. America could afford to design the Sherman as a medium tank, adequate armor protection, adequate main gun, adequate mobility, and then focus every effort on reliability, maintainability, and above all, mass production at unprecedented scale. The Sherman was not the best tank of the war by many individual technical measures. German Panthers and Tigers outgunned it substantially. Soviet 34s matched or exceeded it in several important specifications. But the Sherman was good enough for its intended purpose, and crucially, America manufactured approximately 50,000 of them. Japan could not possibly adopt that design philosophy. Every Japanese tank had to be ruthlessly optimized for resource efficiency. Every component had to be designed around material constraints and manufacturing limitations. You could not simply make something good enough and build 50,000 of them. You had to make something as combat effective as humanly possible with severely limited resources and build hundreds at most. This enforced a cascade of painful compromises. Lighter armor meant vulnerability to enemy anti-tank weapons. Smaller, less powerful engines meant reduced mobility and slower turret traverse. Lower velocity guns meant diminished anti-armor capability. Each individual compromise appeared rational given the constraints, but the cumulative effect produced fighting vehicles that struggled desperately against American and Soviet armor in the few direct engagements that occurred. The post-war period would reveal the full, staggering extent of the industrial disparity. American production statistics released after Japan's surrender showed that the United States had manufactured during the war years 88,000 tanks and self-propelled guns, 297,000 aircraft, 41 billion rounds of ammunition, 64,000 landing craft, and millions of trucks, jeeps, and other vehicles. Japan produced approximately 6,000 tanks across all types during the entire war. 6,000 versus 88,000. The ratio stood at roughly 15-1, and that calculation did not account for quality differences, logistical support, infrastructure, or the fact that American production accelerated steadily throughout the war while Japanese production declined as resources dwindled and facilities were destroyed. But statistics, even such devastating ones, do not fully capture what Hara and his engineers experienced during those months examining the Sherman. Numbers remain abstract, easy to dismiss or rationalize. What they touched daily was concrete, precisely machined gears they could hold, consistent metallurgy they could measure, robust assemblies explicitly designed for field maintenance by minimally trained personnel. They could physically feel the industrial capacity behind every component. One of the engineers, in a diary, entry discovered decades after the war, attempted to articulate what the experience meant to him personally. We were told repeatedly that America was a nation of merchants and soft people. We were told their military equipment was crude and mass-produced without care. But there is nothing crude about what we have found here. Every part shows meticulous attention. Every specification is met without exception. This is not crude work. This is sophisticated manufacturing executed at a scale we simply cannot match. The crudeness exists not in their products, but in our fundamental misunderstanding of what they were capable of producing. Another dimension of the revelation involved maintenance and field repair procedures. The Sherman was explicitly designed for maintainability under combat conditions. Its transmission could be removed and replaced in approximately 4 hours by a reasonably trained crew, equipped with proper tools and a replacement unit. Components were rigorously standardized. A replacement part from any Sherman would fit any other Sherman of the same model variant without modification or adjustment. Tolerances were deliberately set to allow for field conditions and imperfect repair facilities while maintaining reliable function. Japanese tanks, by contrast, often demanded highly skilled mechanics for even routine repairs. Parts were less standardized. Components from one Chiha might not fit another Chiha without careful fitting and modification. This reflected limited production scale and continuously evolving designs as engineers tried to improve performance, but it meant that damaged Japanese tanks were far more difficult to return to operational service under field conditions. The Sherman's fundamental design philosophy assumed abundance. Abundance of replacement parts, abundance of fuel, abundance of ammunition, abundance of trained maintenance personnel. A Sherman crew could reasonably expect robust logistical support to be consistently available. Japanese tank crews could make no such assumptions. By 1944, Japanese logistics throughout the Pacific were collapsing completely under relentless American air and submarine attacks. Tanks sat immobilized for lack of fuel. Damaged vehicles were abandoned because critical repair parts could not be delivered through interdicted supply lines. Hara came to understand that the Sherman transmission represented far more than a mechanical component. It was a window into American strategic thinking. The United States was deliberately fighting a war of material attrition, supremely confident in its ability to outproduce any conceivable opponent. The Sherman was not designed to be superior in any single performance metric. It was designed to be producible at scale, maintainable under field conditions, and available in overwhelming numbers that would make individual tactical superiority irrelevant. Japan had designed weapons for an entirely different kind of war, a war of decisive battles, tactical brilliance, and maximally efficient use of severely limited resources. Japanese military doctrine emphasized surprise, aggressive action, and superior fighting spirit, precisely because Japanese strategic planners understood they could not possibly win a protracted material struggle. The strategy had worked brilliantly in the short term. Early victories had been spectacular and exceeded even optimistic projections. But the war had evolved into exactly what Japan could not afford: a long, grinding conflict of attrition where industrial capacity mattered far more than tactical virtuosity or fighting spirit. The engineers at Sagamihara had been confronted with physical, measurable proof of this strategic reality. They could not dismiss it with arguments about fighting spirit or cultural superiority. The gears and bearings did not respond to ideology. They operated according to immutable laws of metallurgy and mechanics. Understanding those laws completely could not overcome, lacking the industrial foundation necessary to implement them at a meaningful scale. For some of the engineers, this realization carried an almost liberating quality in its brutal clarity. One engineer, interviewed extensively by American technical teams after the war, stated, "Until we examined that transmission in detail, when we failed to meet production targets or when our equipment underperformed in combat, there was always the unspoken question, are we not working hard enough? Are we not sufficiently skilled? Are we somehow failing in our duty?" Sherman showed us clearly that we had been asking entirely the wrong questions. The problem was never effort or skill or dedication. The problem was that we were attempting to accomplish with $3 what properly required 30. This experience would profoundly influence post-war Japanese industrial development. Many of the engineers who examined the captured Sherman would go on to play significant roles in rebuilding Japan's industrial base during the 1950s and 1960s. They carried forward a hard-won understanding of what modern industrial capacity genuinely required: sophisticated machine tools, rigorous quality control systems, manufacturing standardization, supply chain depth and redundancy, metallurgical consistency, and systematic skilled workforce development. These lessons would contribute substantially to shaping Japan's remarkable economic recovery. But in August 1945, as Hara prepared and submitted his final technical report, the immediate lesson was simpler and infinitely more devastating. Japan had entered total war against an opponent whose industrial capacity it had fundamentally, catastrophically misunderstood at every level. You could not make your way past that misunderstanding. You could not compensate for it through courage, tactical skill, or self-sacrifice. It was a material fact as solid and undeniable as the self-ices. Precisely machined steel gears spread methodically across the workbenches. The story of Japanese engineers examining a captured Sherman tank might appear at first to be a narrow technical episode, an obscure footnote in the vast history of the Pacific War. But it represents something far larger and more significant: the moment when highly educated, skilled professionals confronted the actual reality of the war their nation was fighting, stripped of propaganda, ideology, and comforting misconceptions. These were not ignorant soldiers fed propaganda without critical thinking. They were engineers with prestigious university degrees, men who thoroughly understood mechanical principles and metallurgical science, professionals who had successfully adapted Western technology numerous times before the war. Their inability to replicate the Sherman at scale was not due to lack of intelligence, effort, or dedication. It stemmed directly from structural realities about industrial capacity, resource availability, and manufacturing infrastructure that no amount of determination could overcome. This pattern repeated across the Pacific War in various forms, each iteration forcing similar reckonings. Japanese soldiers encountering the sheer abundance of American logistical supply. Japanese naval officers watching American shipyards produce vessels faster than submarines could sink them. Japanese civilians were transported through American territory as prisoners of war, witnessing endless productive farmland and massive factories operating at scales they had never imagined possible. Each encounter forced individuals to reconcile what they had been taught with what they could directly observe and measure. The Sherman transmission serves as a nearly perfect metaphor because it was simultaneously mundane and profoundly revealing. It was not a secret weapon or revolutionary advanced technology. It was an ordinary component in an ordinary tank, designed specifically to be produced in vast quantities with consistent quality. That very ordinariness amplified the revelation if even this standard equipment exceeded Japan's capacity to replicate at meaningful scale. What did that imply about the overall balance of industrial capability? War encompasses many dimensions: tactical, strategic, ideological, moral, cultural. But underneath all of them lies an inescapable material foundation: the capacity to produce weapons, feed armies, sustain logistics networks, and replace inevitable losses. Nations can sometimes overcome material disadvantages temporarily through tactical brilliance or favorable strategic positioning, but there are absolute limits. When the material disparity grows sufficiently large, no amount of courage, skill, or sacrifice can bridge that gap indefinitely. The Japanese engineers at Sagamihara discovered those limits by systematically taking apart a machine and attempting to understand how to construct another. What they learned was that understanding alone is insufficient. You need steel mills and precision machine tools and reliable electrical grids and trained workforces and deep supply chains and dozens of other foundational elements. You need a complete industrial ecosystem, not merely engineering knowledge and technical skill. This is precisely why their story retains significance 79 years after those events. It reminds us that wars are not won by warriors alone, but by factories, foundries, machine shops, and assembly lines operating at sustainable scale. It demonstrates clearly that confidence and courage cannot substitute for industrial capacity and resource depth, and it illustrates how propaganda and carefully controlled information can obscure uncomfortable realities, but only until someone takes precise measurements of the gears and calculates the actual tolerances required for production. The Imperial Army Technical Bureau at Sagamihara was eventually destroyed during American bombing raids in 1556, the final months of the war. The captured Sherman tank was likely scrapped after Japan's surrender. The detailed technical reports were scattered, with some portions preserved in archives and others lost forever. Lieutenant Colonel Hara returned to civilian life and worked in Japan's recovering automotive industry, rarely speaking publicly about his wartime experiences. But the lesson remains, preserved not in the physical artifacts, but in the documented realization of men who touched the evidence directly. They learned what their nation's leadership had refused to acknowledge, that modern industrial war is won in the factories before the first shot is fired. The machines, the infrastructure, the resources, the trained workers, these determine outcomes far more than tactical doctrine or fighting spirit. Understanding this truth came too late to change anything for Japan, but it stands as a permanent historical lesson about the relationship between industrial capacity and military capability, about the dangers of self-deception in strategic planning, and about the ultimate futility of courage confronting overwhelming material disparity. In that sweltering warehouse in Sagamihara, examining precision gears they could not replicate, Japanese engineers confronted a truth their nation had spent years denying. The war had been lost not when the first bombs fell on Pearl Harbor, not when Midway turned the tide, not when the Philippines fell or Okinawa was invaded. It had been lost in the comparative outputs of steel mills, the production rates of machine tool factories, the training capacity of technical schools, and the resource extraction from mines and wells. Everything else, all the battles, all the sacrifice, all the determination was simply working out the inevitable consequences of that fundamental imbalance. The Sherman tank's transmission, spread across those workbenches in careful sequence, told that story more clearly than any strategic analysis or statistical compilation could. It was the physical embodiment of an industrial capacity so vast that even understanding it completely could not bridge the gap. And in that gap between understanding and capability lies one of World War II's most profound and sobering lessons. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.